I do know about the water. All right, guys, we're going to get started because I barely finished in first and second, which means I probably won't finish in here. So we have a normal week this week. I think the first real normal week we've had this 9 weeks so far. We'll have lessons today, tomorrow, Wednesday, tutoring on Thursday, and group bonus on Friday. You have a problem set due at the end of the week that is from the first 3 lessons, the one from last week, then today's and tomorrow's. MATLAB 3 is due next week at the beginning of the week, so you still have about a week left if you didn't have a chance to work on MATLAB 3. That's coming up in a week from tomorrow. I think it's Tuesday. Well, yeah, we don't have school Monday, so Tuesday of next week. Today we're looking at what are called the 4 subspaces of linear algebra. So a couple things we're going to need for these 4 subspaces is to review a couple of words. Rank is just number of pivots. So when we talk about the rank of a matrix, it's just the number of pivots. So if we do elimination, we can count those. Dimension is the number of vectors in a basis. And we talked about basis, I think in the last lesson. Basis is the smallest number of vectors needed to describe all the others by linear combination. So like think in R2, we need 2 of them, like 1, 0, and 0, 1. And with those 2, we could get all the other vectors in R2 by doing linear combinations. Or those aren't the only ones, but you could do any 2 independent vectors in R2. You can get the rest of them by linear combinations of those 2. So that's what we mean by a basis. So when we say something is 4-dimensional, it means there's 4 vectors in a basis. We need 4 independent vectors to describe all the other vectors in that space. All right, so we have 4 main subspaces of linear algebra. 2 we've already talked about. So we talked about the column space. It's a subspace of Rm. Okay, even though it's the column space and A is m rows by n columns, don't get confused. There's actually going to be m elements in every column. Think the number of rows tells me how many numbers are in the column. Right, so that's what we mean by a subspace of Rm, is it's going to have m elements. Okay, however many rows, there's 2 rows, there will be 2 elements in the columns. If there's 5 rows, there will be 5 elements in every column. It answers the question, what types of B's could I get? So this will be n by 1. B would be m by 1. So it's another reason it will be a subspace of Rm. The column space is telling me what kind of B's I get, which have m elements in them as well. Okay, but really the column space is just all the vectors I can get by linear combinations of the columns. The null space is a subspace of Rn. Okay, and it's answering the question, what x's make ax equals 0? This is probably the one we've had the most experience with so far, because we've found when ax equals 0 quite a bit. It's a subspace of Rn because think it's the types of things we can plug in here to x. So we will have n elements in it for me to be able to multiply A times those vectors. It'll have to be n elements. Okay, the row space is also a subspace of Rn. The row space is just like the column space is the multiples of the column, the linear combinations of columns. What types of things can I get? The row space is when I take linear combinations of the rows. What kinds of things do I get? It's really a same idea as what type of C's could I get if I was multiplying from the left instead by my unknowns. So think if I had like X, Y, and Z, and I was multiplying from the left of A, whatever A is. And I would get all these constants, C1, C2, C3. We would have to make them rows to do this, right? If A is like 3 by 3, I cannot multiply a column on the left-hand side that's 3 by 1. I would have to do a row that's 1 by 3, and I will get another row that's 1 by 3, for example. So that's why they're transposed in that equation, is instead of taking columns multiplied on the right, we're saying, what if I did these similar equations, but I wanted to multiply on the left? You would transpose them so I'd get row vectors instead of columns. A lot of times it's easier, since we've already kind of talked about AX equals B and stuff like that. If we transpose both sides of this equation, remember that Y transpose A parentheses transposed, I would switch the order, and so this would be A, T, Y. The transpose of C will just be C.
Oh my God, dude.
Huh. Okay, transpose of C is just C. So the row space you could also think as the column space of A transpose. So if you start to get to where you're like, I think I have a decent idea of what the column space is, the row space is just the same thing of the transpose of A. Okay, which should make sense because it'll take all the rows and make them columns, and then I can look at the columns. And then the left null space is the same idea. This time I'm multiplying from the left times A by a row vector times A to see what will give me a row of zeros. And doing the same thing, this is A transpose Y equals 0. So we could think of this as the normal null space of A transpose. So again, if you're like, I think I kind of understand the null space, left null space is confusing. It's just the null space if I were to take A, transpose it, and now look for the things that would make AX equals 0 or AY equals 0 or whatever. Okay, the row space is a subspace of Rm, M being the number of columns in A. So it'll be the number of rows in A transpose. I mean, the number of rows, yeah, in A transpose. So we're looking for a subspace of Rn there. The left null space is a subspace of Rm. That's going to factor into something that we'll do in a different lesson. But you just want to realize if A is not a square, there could be different numbers of elements in the vectors there. They won't all be the same size necessarily. Okay, so again, we already started to discuss the null space and column space. Row space is just the linear combinations of rows. Okay, it's also the column space of the transpose of A. So if you get more comfortable with column space and you want to think of it as just the column space of the transpose of A, and whatever I do to find the column space, I could do the same thing to A transpose, and that's going to be the row space of A. Left null space, same idea. If you're like, I think I can get the null space of A, we'll transpose it and get the null space of that, and that's the left null space. Okay, it's the things that you multiply from the left by to get 0, as opposed to multiplying from the right to get 0. Okay, so the 4 subspaces factor into what's called the fundamental theorem of linear algebra. So we had a fundamental theorem of calculus, had to do with how we solve definite integrals. We had a fundamental, it was in 2 parts as well. We had a fundamental theorem of line integrals from multivariable calculus. Here's a fundamental theorem of linear algebra. We're only going to do part 1 today. The whole thing deals with connecting the subspaces. So the first one is connecting all the dimensions of the subspaces. Again, meaning what do I need to come up with a basis for these 4 things? A basis is the kind of basic thing we would use to describe the space. If I'm like, okay, here's a basis, I could then kind of start to understand what the space looks like. So the dimension of the row space and the column space will be the rank of the matrix, meaning the number of pivots. If there's 2 pivots, row space and column space will both be dimension 2, meaning I'll need 2 independent vectors to describe the row space, 2 to describe the column space. It does not mean they have the same number of numbers in each vector. It means they have the same number of vectors in the basis. Okay? And whatever it is the number of pivots. The null space will be dimension n minus r. The null space, again, is the one we've been doing the longest. It's the number of free variables. Free variables are what give us the ax equals 0 stuff. So think if I've got n columns, r pivots, subtract, that's how many free variables you're going to have. So that should be the one that's kind of logically the easiest to get at this point, is there's n minus r is the dimension of the null space. It's the number of free variables, is the number of vectors you'll get in the null space basis. The left null space, again, similar idea, think if we were to transpose. Now there's m columns. Subtract the number of pivots, and there's going to be that many free variables for the transpose of A, if we were to find the same thing. So that's the whole first part. It's just what's the dimension, the basis, the dimension of each of those spaces, meaning how many vectors are in each basis. Okay, and then part 2 will connect a different aspect of those 4 subspaces there. So we're going to look today just basically coming up with a basis for the 4 subspaces. We're going to start with a U, a reduced form of a matrix already reduced, because then that takes out some of the first parts that we already technically can do, but we can then focus just on this. So say this is the matrix I'm interested in. First thing is I should be able to tell the rank from U really easily. Rank here is 2. There's a pivot in column 1, a pivot in column 4. Which means the dimension is the rank for a row space. It's 2. Meaning if I'm coming up with a basis for the row space, I need 2 independent vectors for which all the other vectors in that space would be linear combinations of those 2. So I would take 2 independent rows that I see. It should be really obvious in its U form, because the independent ones are the ones that are not all zeros. Oops. So my first 2 rows would be a basis for the row space. So I've got this 2-dimensional subspace of R5. R5 because there's 5 numbers. But it's only 2-dimensional. So think like a plane in R5, essentially. I've got all these vectors in R5, but they have to fall on the same kind of plane as these things. Okay, whatever that looks like in 5 dimensions. They'd have to be linear combinations of these. Yeah. They will be the rows that have the pivots as well. But yeah, basically the non-zero rows. But rows with pivots is the same idea. So yeah, that'll work as well. So it'll be the rows with the pivots in them. Okay, there should be 2. We have 2. So those numbers should match there. So main ideas with row space, dimension should be the same as the rank. Again, number of pivots. The non-zero rows of U will be a basis for the row space of A as well. So even if we started with something else and we reduced to U, they'll be a basis for both. Okay. They're a basis for the row space of U and for A. Since all I do to get from A to U is I take linear combinations of the rows of A, I'm not really changing the row space, right? That is one of the kind of basic ideas of a vector space, is that when I take linear combinations of those vectors, I get more vectors in the same space. So when I do row eliminations, I'm not changing the row space because I'm just taking multiples of rows, adding them to other rows, and getting more vectors that are also in the row space. So once I find it for U, whatever A originally was, it's the same thing, row space-wise. Okay, that won't have changed. Okay, same matrix if we look for the column space. The dimension is also the rank, which again here is 2. It's the same matrix, so it's going to have the same rank, same dimension for the column space, which means we're looking for 2 vectors, 2 column vectors that are independent of each other. I would choose the pivot columns. They're not your only choices. If there's 5 columns, there are going to be other ones that are independent. The pivots, you know, will be independent. So like on one like this, you may be able to tell like column 1 and 2 are not independent of each other. That's easy enough to see, and I don't want to choose 1 and 2. Or you might say 1 and 5 are independent. So I could choose 1 and 5, and that would work. In general, if it's not so obvious, the pivots are your safe choice. Choose the pivot columns. They will be independent. If they weren't, when you did elimination, you would end up with multiples of each other, and they would not both be pivots. So like 1, 2, and 3 are multiples of each other because when I do elimination, they didn't necessarily have to be before. But that's what's going to cause that to happen, is the same multiples of like the second elements cause the things to zero out. The same multiples of the thirds cause those to 0, which is what gave me those kind of multiples of each other. So I want to choose the pivot columns. Not the only choice, but those are kind of your best choice there. Here, be careful. The dimension is R. The pivot columns of U will be a basis for U's column space, not A. We did not get to elimination by taking linear combinations of the columns. We did the rows, meaning we've changed parts of the columns, but not other parts of the columns. So we don't really have columns that are in the same vector space as the original, because we kind of changed parts of them. So you want to avoid using the columns of U as a basis for the columns of A. But choose the same columns of A. So like if the pivots were in column 1 and 4, go back to A and choose column 1 and 4. Those are going to be 2 independent vectors. So we can still use that the pivots were in 1 and 4 of U, just don't use the U ones, use the A's. They go back to your original if I want a basis for A. All right, null space. Here we have the dimension is going to be the rank, n minus the rank. So we have 5 columns, the rank is 2. We're going to end up with 3 vectors in our basis. And again, this is what we've already done. There's 3 free variables. That's going to be the same thing. x2, x3, and x5 are our free variables. Those numbers are the same. Okay, why we're getting 3 is because there's 3 free variables. And so we get a basis by doing what we did to find the special solution. It's the same thing we've already done. We just didn't call it a basis. So x2 is 1, x3 is 0, x5 is 0. Solve ux equals 0. Get a vector. Okay, set x3 equal to 1 and x2 and 5 both equal to 0. Solve ux equals 0, get a vector. Set x5 equal to 1, x2 and x3 equal to 0. Solve ux equals 0, get a vector. And those will be your 3. Those same ones we did that were the special solutions that were a part of our complete solution. Those 3 in this case would be the basis vectors for your null space. And I'm not going to go through them all because we won't have time. But you guys, we've done that before. You hopefully can set those equations. 4x4 plus 8x5 equals 0, and then x1 plus 3x2 plus 5x3 plus 7x4 plus 9x5 equals 0. Solve them, you'll get 3 vectors here. Those are your special solutions. Those are also the basis vectors for the null space. You don't have to put them as multiples. That's what a basis means. So you omit that part that we would have done in the solution and say the basis vectors are this one, and this one. Again, those are not your only options, but that's the way I would find them. There's a lot, again, multiples of them and stuff would work too. Okay, so dimensions n minus r for null space. Your special solutions are your basis. And just remember ux equals 0 and ax equals 0 at the same place. So again, once I've done elimination, I don't have to go back to A to figure stuff out. Solving ux equals 0 is going to give me the same vectors as ax equals 0. Okay, and then the left null space tends to be the one that confuses people the most. Dimension should be easy. Dimension is m minus r. So we have 3 minus 2 is 1. Right? 3 rows, rank 2, we'll have 1 vector here. So I'm trying to think, what would I multiply on this side to give me zeros here? So what row would I multiply by each column? And I should get 0 every time. In reduced form, it should be really easy. Any row of zeros, you basically put anything you want in that corresponding location, right? Like, since my third row is all zeros, I'll just put the third element as anything I want, the other 2 as zeros. And now if I take the dot product of that and 1, 0, 0, or 3, 0, 0, or 5, 0, 0, or 7, 4, 0, or 9, 8, 0, I'll get 0. Okay, the 1 is arbitrary. It could be any number. I wouldn't put it as a 0. It should be an independent thing like 0, 0, 2 or 0, 0, 3 or whatever you want it to be. So if you have a row of zeros in your eliminated form, that's going to be a basis for the left null space of U. If you've got multiple rows of zeros, that's what's going to lead you to a higher dimension, right? If I had 2 rows of zeros, you'd add a row, which means m would be 4 minus 2 would have been 2. I'd end up with another vector that would correspond to that one as well. Like those 2 would both work, right? So if I added rows of zeros, I would end up with more choices. Your dimension should go up and all that stuff. This is not the left null space of A. If we did an elimination, this is the left null space of U. Similar to the column space, when we mess with the rows here, we'll mess with the left null space. So for the left null space, dimension is m minus r. That part should be easy. This first part is for U. Okay, for U, just the first r components of the basis, just make them 0. And then you can make the other stuff anything you want. For A, what I do is I think of the combination that gave you your rows of 0. So if we have A, and we reduce it down, and I have U, and remember we'd end up with things like B1 or B2 minus 2B1. and B3 minus 3B1 plus B2 or whatever. If my U ends up with rows of zeros here, those combinations, that is the left null space. That's what we are looking for, is when I get zeros on this side, this tells me 1B2, negative 2B1, and 0B3. B3 had nothing to do with that one. This is in the left null space. Okay, that's the combination that gave me a row of zeros. It's taking 1 of row 2 minus 2 of row 1. So in the first spot, I'll put the minus 2 that I want to multiply by the first row. In the second spot, I'll put the 1 that I want to multiply by row 2. In the third spot, I'll put a 0. And I know that when I added 1 row 2 to negative 2 row 1, I got 0. I would also know 1 row 3, negative 3 row 1, and 1 row 2 would also be in the left null space. Because when I took negative 3 times the first thing, plus 1 times the second, plus 1 times the third, I also got a row of zeros. So rather than go back and solve the null space of A transpose, just keep track of what rows. We're supposed to be writing that anyway. I'm doing row 1 plus row 2 and row 3 minus row 4 and whatever. Keep track of what rows gave you zeros. Every time that happens, you have a new combination that is a left null space vector. Okay, and we'll do some examples, so hopefully that makes a little more sense. But if it doesn't, ultimately you can just transpose A, find the free variables, set them equal to 1s and 0s, and do the same thing. Okay, so notice for RU, our row space and null space were both vectors with 5 elements. They were subspaces of R5. Okay, our row space had 2. Our null space had 3 basis vectors. Put them together, we had our 5 total. But they each have 5 elements in them. Our column space and left null space both had 3 elements in them. Each of the basis vectors had 3. They're both subspaces of R3. That's what we mean by that RM, Rn stuff, is that our row space and null space, they should have the same number of elements as the rows have. Our column space and left null space should have the same number of elements as the columns have in them. And what we'll see in our next lesson is there's a relationship there. The column space for ours had 2 vectors in its spaces. The left null space had 1. They're both in R3, and notice put them together, and I have 3 vectors in the bases that are put together. So that's going to be part of part 2 that we'll see in the next lesson. But for now, you just want to be able to tell, for some reason, people start looking, and every vector will have 3 in it that you're talking on the 4 subspaces, just because they're looking at the columns. Or every vector will have 5, because you'll see those rows with 5 numbers, and you'll put 5 numbers in every single thing. You don't want to do that. Okay, you want to be able to tell columns have 3 numbers, so the column space should have 3 numbers in their vectors. Okay, so kind of generalize what we're doing here. I would take A and reduce it to its epsilon form. Okay, the little stair step U thing. A and U have the same row space, because every row of U is just a linear combination of the rows of A. So you haven't changed the row space at all. So either use the first R rows of U, or pick R independent rows of A as your basis. It should both be the same. Not the same vectors, but the same basis, the same vector space that we're looking at. The column space of A and U are not always the same. They might end up being the same, they might not. So in general, once you've gotten to U, find the pivots and go back to A and pick those same columns from A as your basis for the column space of A. Don't pick columns of U. It could happen that they are the same, but it's not a good rule to depend on. Okay, null space should be, I think, the most work of any of them, because you've set X is equal to all this stuff, but also the one you're most familiar with. We've been doing this one the longest. So we've been using this for a while. I want AX equals 0. I just reduce, find where UX equals 0. That's the same place. Okay, and these are your special solutions that you're looking for. So for every free variable, you should have another independent vector in the null space. And then for the left null space, I would keep track of the multiples of rows that eliminated to give you rows of zeros. Every row of zeros you have, you should have a vector that gave you that row of zeros. Or find the null space of the transpose of A. Okay, literally transpose A, find the free variables, set them equal to 1s and 0s. That's the left null space. That to me is a lot more work than if we've already done elimination on A, why have to do it again on A transpose and all that stuff. I would just use what we did on A to find those instead. But some people find this easier to comprehend, to understand. So they use that. That's fine. All right. So again, tomorrow we're going to kind of, or in the one of the next lessons, we're going to do part 2. And it's relating this idea that like the row space and null space are both subspaces of Rn. And notice if we have a basis that has R vectors in it, and then we add n minus R vectors to it, we'll have n vectors. If I combine the two spaces, I'll have n vectors. As long as they're independent, n independent vectors in Rn are a basis for all of Rn. So what we'll see is if I take those row space vectors and those null space vectors and I put them together, I will have a basis for all of Rn. Okay, but again, that'll come later. So that's kind of where we're heading, that you should start to kind of see some of that in the homework here. And the reason we look so much about vector spaces is we want to generalize what we're finding, generalize what we're seeing. It's easy when you're doing these like 2x2s or 3x3s or 2x3s or whatever to go, why would I need to understand all this when this is, it's kind of easy to start seeing what's happening every time. That's true. Linear algebra is geared towards being able to solve a problem of any size, which is why it works so well with computers and things like that. So if we were to start seeing really large matrices, you don't want to just have to like poke at random things and see what happens. You want to have this kind of generalized solution where I'm like, okay, I've got this 11 by 17 matrix. I've got 11 equations with 17 unknowns in them. What do I need to do to solve? What types of solutions will there be? Will there be any solutions? You're trying to kind of generalize this to any size that we look at. Rather than just kind of like do random stuff because there's not very many choices because we're doing small examples. All right, we're going to end with a couple examples. We're just going to find the basis for each of the 4 subspaces. So first thing I would do is elimination. So I'm going to take row 2 minus 3 row 1. And this is going to give me U 1, 2, 3, 0, 0, 0. Rank is 1, right? There's 1 pivot. M is 2, N is 3. 2 rows, 3 columns. Okay, for the column space, dimension is rank. It's 1. This should be a subspace of R2. There are 2 elements in the columns. There should be 2 elements in my basis vectors as well. I only need 1 of them. Oops. Typically, I would choose the pivot column from A, not U. Pivot is in column 1 of U. I would choose that same column in A, 1, 3. Because there's only 1, you really could choose any column of A. Any column by itself, unless it was zeros, would be an acceptable independent column, right? Here, generally, I would stick to the pivots because once you get 2 or 3 or 4, it won't be so obvious which ones are independent and which ones are not. So I see that the pivot is in column 1 of U, so I go back to A and I choose column 1. Okay, row space, its dimension is also 1. Okay, same as the rank. So I'm looking for one independent row. I would choose the non-zero row of U. Again, since we have a dimension of 1, I could choose any non-zero row of A as well. But typically, if there's a bunch of rows of A, I would look at U and choose the pivot rows or the non-zero rows. And those are the ones I would know would be independent. Notice both of them are one-dimensional. So like column space here, it's a line in R2, right? A one-dimensional subspace of R2. The row space is also a line, but in R3. Okay, so a line in three-dimensional space rather than on an XY plane. So it's also a line, a one-dimensional subspace of R3. Okay, null space. Dimension is n minus r, so it'll be 2. And notice we have 2 free variables. So I would let x2 be 1, x3 be 0, and then solve our one equation that's there. x1 plus 2x2 plus 3x3 gives me 0. So x1 should be negative 2. So I have negative, this is basis. Negative 2, 1, 0. And this is also one we should be able to check pretty easily. Multiply that by any row of A and you get 0. I would then let x2 be 0 and x3 be 1. And solve that same equation and you get x1 is negative 3. Right? Negative 3 plus 0 plus 3 gives me 0. So we have negative 3, 0, 1. Two-dimensional subspace of R3. It's a plane. Okay, the null space here is a plane in R3. Okay, and then the left null space dimension is m minus r. 2 minus 1 is 1. And I would just look at what gave me that row of zeros. It was taking negative 3 row 1 and 1 row 2. And notice that's also a subspace of R2, another line, actually a line perpendicular to the one we got before, right? Negative 3, 1, and 1, 3. Our row space and null space are both in R3. One is a line, one is a plane. They are also perpendicular. Okay, and that'll, again, that's going to be part of what we see in the next part of the fundamental theorem, is that there's still more relationships there, but that's kind of our basic idea so far. Okay, another example, 1, 2, 3, 2, 4, 6, 1, 1, 1. So I'm going to take row 2 minus 2 row 1 and row 3 minus row 1. So I can do elimination. 1, 2, 3, 0, 0, 0, 0, negative 1, negative 2. Okay, and typically you might want to have switched row 1, 2, and 3 to have that triangle, but we can identify the pivots, which is really what we're looking for. There's 2. M equals 3, N equals 3. Right? There's 2 rows that are non-zero. We have 2 pivots. So for row space, our dimension is R2. I mean, sorry, for our column space, our dimension is 2. We want to choose 2 independent columns. I would choose the pivot columns, but not from U, from A. So our pivots are in 1 and 2. So I'm going to choose columns 1 and 2. 1, 2, 1, and 2, 4, 1. I forgot to put this as the basis. They should be independent. They are. Okay, you can tell 2 times 1 is 2, 2 times 2 is 4, but 2 times 1 is not 1. So they're not multiples of each other. They're definitely independent. For the row space, my dimension is also 2. And again, I would literally just choose the non-zero rows, 1, 2, 3, 0, -1, -2. You can go back to A and choose the first and third row of A. They're in the same plane. Both are two-dimensional subspace of R3. They're the same two-dimensional subspace of R3. Whether you choose from A or U, it doesn't matter for row space. Null space. Dimension is n minus r, so 1. And again, we've got one free variable, x3 set to equal to 1. So I'll have negative x2 minus 2 is 0, which means x2 will be -2. And then we have x1 minus 4 plus 3 is 0, so x1 will have to be 1. So I have 1, -2, 1. And again, multiply that by any row of A and you should see 0. 1 minus 4 plus 3, 2 minus 8 plus 6, and 1 minus 2 plus 1. We only need 1 this time. Subspace of R3, it's a line. Then the left null space is dimension, again, m minus r, so again 1. So I want to look at the row that turned to zeros. And all I did was I took -2 times row 1, 1 times row 2, and 0 times row 3. And that's what gave me that row of zeros. If I multiply this times A on the left, if I take dot products of that and the columns of A, I'll get 0 now, right? -2, 1, 0 times 1, 2, 1. Times 2, 4, 1, and times 3, 6, 1. That gives me 0. One-dimensional subspace of R3. It's a line as well. Okay, last example. If I don't, I'm going to finish it whether the bell rings or not. But last example, 1, 2, 3, 2, 4, 6, 3, 6, 9. I'm going to take row 2 minus 2 row 1 and row 3 minus 3 row 1. 1, 2, 3, 0, 0, 0, 0, 0, 0. Rank is 1. M is 3, N is 3. Column space. Dimension is rank, it's 1. I want one independent column. I would choose the pivot column, 1, 2, 3. Choose from A, not from U. Okay, so like the column space of U is the x-axis, right? I can only get x non-zero, then Y would be 0, Z would be 0. The column space of A is one-dimensional. It's a line, it's not the x-axis though. I can clearly get non-zero Y's and Z's from A. So don't choose 1, 0, 0. Okay, it's 1, 2, 3, or the other ones will work here. Row space, dimensions also 1. I'm going to choose a row 1. Okay, both of them one-dimensional subspaces of R3. Both of them are lines. Null space, N minus R, dimension is 2. So I'll let x2 be 1, x3 be 0, and x1 would again be -2. This is the same one we just looked at the first example. I'll let x2 be 0, x3 be 1, x1 would then be -3. So we have the same basis as we had for one of our other ones. So I'd have -2, 1, 0, and -3, 0, 1. And then left null space, m minus r, so 3 minus 1 is 2. And again, now we got 2 rows that zeroed out. My basis, I would just choose the combination of rows that caused that to happen. So row 2 happened because I took -2 times row 1 plus row 2 and no row 3s. Column 3 happened because I took -3 times row 1, no row 2s, and 1 row 3. And that's what caused those rows of zeros to occur. So for each row of zeros you get in the eliminated upper echelon form, you should have another basis vector. This is a 2-dimensional subspace of R3. It's a plane. Okay, so we have a few seconds left. I actually finished, but I had to kind of speed up there at the end. So if you guys need anything, let me know. If you don't, you guys have a good afternoon. I'll see you guys tomorrow. I'll post this video. If I went too fast there at the end, you need to go back to any examples. I'll post a video so you can do that. But that's it.
Thank you.